Okay, so you can use your yellow sheet to write some things down, and you can use, your notebook paper. We can, or your photograph paper. We're going to kind of go back and forth between some things. But for sure, you need to have somewhere that this is the pattern for us to recognize a limosome. There's like a little squiggly above one of the letters, which makes it pronounced as limosome. Okay. French word. I like to call them limacons, but I think they're supposed to be pronounced limacons. Okay, so I will try this year to say it the correct way. Um, let's first talk about, we all know this, sine and cosine determines what? Say a letter? Okay, where do we have symmetry? Okay, whoops, I can spell. We know that sine correlates to vertical symmetry, and cosine will correlate with horizontal symmetry. That is going to be the same for these limosomes. Okay. How about that addition versus subtraction? Did anybody notice how that affected your graph? Darby, what observation did you make? Okay, so a majority of our graph goes to either the positive or negative side. Okay, and I'm going to kind of generalize it that way. I like that you said that, Darby, because it puts it in more of a general form. Okay, if we're talking about a curve with a cosine, we're going to have horizontal symmetry. So your limosome is going to be either mostly to the right or mostly to the left. If we have a positive between A and B, it's going to be mostly where? It would be to the right, because that's where the positive, that's what we think of as like positive X values, even though we don't have X values here, okay? Or positive R values, I guess we could say. If it's a minus B cosine theta, then the majority is going to go to the left, where we envision, more of our negative numbers. If we have a limosome that has a sign in it, then we're going to talk about up and down, right? If it's a plus B sine theta, majority is going to be up. And if it's a minus B sine theta, majority is going to be down. So that positive versus, that addition versus subtraction, let's call it that. Addition versus subtraction is going to tell us where a majority of our limosome will be. All right. This one was a little tougher to figure out from your activity, but maybe some of you looked it up in your book. What does A plus B stand for? Did you look it up?
In the book, yeah. Well, I don't know if this is correct, but I said it's the distance from the pole.
Okay. That's good. We've been describing that as our max R distance. Okay. The furthest away our limosome will be is when we add A plus B. Now, keep in mind, A and B are always going to be positive numbers. We're viewing like the addition versus subtraction between them, but A and B are both going to be positive. So when you add them together, that's going to be your max distance from R. Okay? And that's going to correlate up here. A majority of our limosome is going to be on a particular side based on this max R distance. That's how far it's going to be from the pole. Okay? All right. A divided by B. Okay? You all notice that you got some funky shapes, right? There's one with like a squiggle. There was one that kind of looked like it was an oval that had been smooshed on one side. Okay? But were you able to figure out why they changed?
Depending on if A was bigger than B or bigger than A or if it was.
Okay, so it depended on how A compared to B. Now, I know that some books, and I can't remember what our book does, to be honest, and that's terrible of me. Some books view it as A compared to B. Some books look at A divided by B, like as a ratio. Okay? We're going to think of A divided by B. We're going to look at the ratio and how it compares to 1 and 2. All right? And that's going to determine the type of limestone. Okay? Now, what is nice about limastones is when we graph them, you're going to do the same critical points every time. Okay? You're not going to have to think about where that first petal was going to be. You're not going to have to think about how many petals. The significant points are going to be very, very straightforward. What you're going to have to keep straight is what each limestone looks like. Okay? So let's go through the 4 different types. All of these are A plus B cosine theta, but you'll just, if we have different versions of limastones, they'll just be oriented a little bit differently. Okay? These are our 4 types. That first one, what does it contain? It has a loop. We're going to call it a loop limestone. Sorry. So when you identify the shape, you're going to tell me limestone, and then you have to tell me whether it is one of these 4. So you would say limestone loop. Okay. We are going to have a loop if A divided by B is less than 1. If A divided by B is less than 1, we will have a loop. This second one, what does it kind of look like? It kind of looks like a heart, right? It comes to this nice, lovely point right here, kind of like you would draw a heart. Except it doesn't really have a heart, right? The pointy right there, but it's close enough to a heart. This is what we call a cardioid, kind of like how cardiology is like the study of hearts, right? This lovely limestone happens when A divided by B equals 1. When A and B are the same, we get that heart shape. What does this shape kind of look like? A bean? A bean, okay. Kind of looks like a bean. You know what this reminds me of? Like, yeah, a dimple. Okay, it is actually called a dimple. To me, it looks like the Pillsbury Doughboy, like when you poke his tummy, like it would dimple in. You know what I mean? That's what I think of every time. He's still around, right?
Yeah.
Okay.
Cure her. It's not like I didn't know what it feels like.
All right, a dimpled limestone happens when A divided by B is strictly between 1 and 2. And then finally, we have this one. It almost looks ovalish, but it's just like a little bit flat right here. Okay, and depending on the A and B, like the bigger it is, the more you can tell that it's really squished, but it's ovalish, but a little bit flat right there. Okay, you'll notice that this is the only one that doesn't have like an indent, right? So we call this one a convex limestone. And this happens when A over B is less than or equal to 2. Greater than would be better. Thank you, Darby.
You drew a greater setup.
I said it right, or I drew it right, said it wrong.
Yeah.
Is that better?
Yeah.
Thanks, guys. Okay, so we're going to do 4 different examples. So you can see all 4 types of limestone. Okay? But what I want you to notice, how many of these go through the pole? Only, we can, either way, go through or touch. Only 2. Which means we have 2 limestons that don't even have zeros. It's cool, right? You don't even have to find those zeros. What? No, there's just no zeros. It's okay not to have zeros. It's just less work for us to do, right? We don't have to find those zeros. Okay? Another reason why limestons are kind of nice is you don't have to find the zeros all the time. Okay? All right, so basically what you're going to need to remember are these names and the order in which they occur. Okay? So here would be my suggestion. You need to remember the order of LCDC. It sounds a lot like ACDC, but with an L. You might not even know who ACDC is, so maybe that's not helpful. Okay? I know that a former pre-calculus teacher from way back in the day used to use the saying that Lou loves dimpled cuties, and that was how she remembered the order. Okay? Love isn't like heart, so Lou loves dimpled cuties. That was her way of remembering it. Okay? My suggestion to you, either use one of those mnemonic devices that I gave you, or find a different one that suits you. Okay? You all are creative. If you need to come up with one that will help you, come up with one. Okay? But for now, let's do some graphing. Okay, so first of all, we see that this is in the form A plus B cosine theta. So we know it is a limestone. Now, let's look at A and B and what their ratio compares to 1 or 2. All right? So 2 is A, 3 is B. We have a ratio of A to B. How does it compare to 1? It's less than 1, which means what about our limestone? It's a what? It's a loop. These are my favorite. I like loops. All right. Using the notes that we wrote down about 10 minutes ago, 5 minutes ago, I don't even know. our max R value, what would it be, Connie? It would be 5. Because that is what A and B are when you add them together. All right. We always say zeros for the end. So let's go ahead and talk about our significant points. Every single limosome that you graph, these are your significant points. Theta is 0, theta is pi over 2, theta is pi, theta is 3 pi over 2, and then back to theta is 2 pi. Those are the only 5 that you need. They're the nicest to plug in, and they give us the nice values on those different axes. I'll come right back, but you notice that all of these graphs, okay, all of the points that are on both the vertical and horizontal axes, they come from, you know, those angles, 0, pi over 2, pi, 3 pi over 2, etc. Okay, so that's all we need to make our shape. Okay, so now it's just a matter of plugging them in. So, let's go. What is the cosine of 0? 1. So we have 2 plus 3 times 1, which is 5. Our first coordinate is 5, 0. Then we move to pi over 2. What is the cosine of pi over 2? 0. So we have 2 plus 3 times 0. So our R value is 2. So at pi over 2, the R value is 2. All right, pi. What is the cosine of pi? -1. So we have 2 plus 3 times -1, which is -1. This is why we get a loop, is because we have a negative R value when we get to one of our significant points. So at pi, we need to move backwards 1. Okay, you will see some patterns, all right? At 3 pi over 2, what's the cosine of 3 pi over 2? 0. So we have 2 plus 3 times 0. So at 3 pi over 2, our R value is 2. And then at 2 pi, we're going to circle back to where we started. The cosine of 2 pi is 1. 2 plus 3 times 1 is 5. And so we come back to that original point. Okay? When you draw your loop, it is important that you draw that loop through the pole. The loop has to go through the pole. And the biggest that the loop is going to be is that coordinate that we plotted with the negative R value. So we start at our first point that we plot. I'm not going to give you like an exact way to figure out how bumpy those are. Okay, just don't make them too extreme. Don't make them too little, but don't make them like really big. Make it so it's, you know, an ovalish shape if we were to exclude the loop. Okay. When we drew this, everyone look up here. When we drew it starting here, how many times did we go through the pole? Once there, twice there. So we have 2 zeros, but guess what? I'm not going to make you find it. Some of you are celebrating. Ms. Holman, why would you not make us do that work? Well, look at this. Don't write this down, just watch me. If we set R equal to 0, we have -2/3 equals the cosine of theta. This is a non-calculator exercise. Are you going to be able to figure that out? No. So we're not going to do it. 2.5 hours. Okay. We were finished with this one, correct? Okay. Any questions on it? Now that you are full of food and tired and happy? Next one. So we know that this is a limacon because it is A plus or minus B, in this case sine theta. Okay, I have a question for you, so I want you to think about before we get into the type. Since this is subtraction and we have sine, where is a majority of our limacon going to be? Think about it, up, right, left, or down. Where is the majority of it going to be? Turn to your neighbor, tell them a word. Well, the answer in one word. All right, it was really exciting because the only word I heard was down, and that's the right answer. Okay, sine means it's going to be up or down, and that subtraction means a majority that's going to be below. Okay, the type of limacon. Am I spelling this right? It's with a D, correct? So I used to spell
There's another I after O.
card. There's like that.
Yeah.
What?
Welcome to the English. I don't know how to look this.
I have spelled this wrong, this word wrong from the get-go. Like, this is probably the first year I remember to put a D instead of a T. Like, it's not a good word. Okay, cardioid. If you spell it wrong, I'm not going to care. How do you know it's a cardioid?
4 divided by 4 is 1.
A divided by B is 1. Okay? Our max R value, Nicole, what would it be? 8. A would be correct. A plus B would be 8. Okay, and we're thinking of B as a positive 4, and there's just subtraction between A and B. Okay? All right, we'll save the number of zeros for the end. Okay, so these are our 5 significant points. Okay, so let's start by plugging in 0. What is the sign of 0? 0, so we have 4 minus 4 times 0. Now, since our max value, R value is 8, and I only have 5 concentric circles right here, I'm going to go ahead and count by 2s for mine, okay? All right, pi over 2. What is the sign of pi over 2? 1. So we have 4 minus 4 times 1. Okay. When you are graphing a cardioid, one of your 5 significant points should be R0. Okay. Pi. What is the sign of pi? 0. So 4 minus 4 times 0. We have another 4. So at pi, we're going to go out 4. That looks pretty boring so far. 3 pi over 2. What is the sign of 3 pi over 2? -1. So we have 4 minus 4 times -1. There's where we get the 8. And then, of course, at 2 pi, we're going to come back to an R value of 4. Okay? Now, is this a triangle? No. We know that at the pole is where we're going to get that point for the heart-ish shape of our cardioid. Right? Make sure that comes to a point. It needs to be nice and pointy. I know I made my coordinate a little. Okay, make sure it comes to a nice point. when you're in calculus, we'll talk about that point being something special. But there that is. Okay, now you can make a love letter to your significant other with a graphical category. No? That's much? Just give you ideas. If only you would have known about this before all the prom proposals, right? Next one. Oh, we didn't do that, did we? Thank you, Kelsey. Let's go back. We didn't find the number of zeros. Kelsey, how many zeros are there?
Does it, okay, so like it meets
Uh-huh.
and then it goes back out, does that count as one or two?
It just counts as one. Because when we get to the pole, we leave it, and so it's like touching it and leaving, so it's just once. Okay, and we actually could identify the zero, right? At pi over 2, we have an R value of 0, that would be our 1, 0. So we could identify that one. This is the only type of limaçon that we would be able to, all the time, figure out what the zeros are. But I probably still won't make you do that. Okay. Now, that's not what I wanted to do. If we were to start at the pole and then draw our cardioid, which I think happens, that's a time where we would have 2 zeros. Like if you would start and then end there, then we would have 2. All right, now for our third example. Okay, so turn to your neighbor, decide what type of limaçon and what the max R value is of the limaçon. You have 10 seconds. Ryan, what type of limaçon is it? And how can you explain what? And can you explain to me how you know that? Okay, if we take A divided by B, it's bigger than 1 but less than 2, so we have a dimpled limaçon. All right? And our max R value would be what, Jen? 7. A plus B would be 7. All right. Please plug in on your own the 5 significant points. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Don't draw your shape quite yet. You can
Lots of 5 points.
Connor, what do you get when you plug in 0?
1.
I'm gonna have to count again by 2's. All right, when we plug in pi over 2, Kanan.
4.
When we plug in pi, Sydney.
7.
When we plug in 3 pi over 2, Kelsey. And then do we make it back to 1? Which side? Okay, so this does not go through the pole, but we have like, we need it to have like a little dimple, but it's a smooth dimple. Okay, so like the cardioid comes to a hard point at the pole. This one has nice, smooth edges everywhere. Okay, but there needs to be some sort of an indent. It's not a very big indent, but it's a little bit of an indent, and it's nice and smooth. And Marissa, how many times do we go through the pole? All right, so we do not have any zeros because we do not go through the pole. It would be my preference that you write none instead of the number 0, because I don't want you to confuse like a 0 of 0 when you're writing 0 zeros. It's a lot of zeros. If there are no zeros, I would prefer you to write none. All right, so Finn, how would we know without graphing it that a majority of this is to the left of the pole? What characteristics about the equation help us with that?
Because it's minus.
Okay, it's minus, so we know it has to be more negative. And what would tell us that it's left instead of down? Okay, so between the cosine and the negative, or the subtraction, we know that it's to the left of the pole. Very good. Last example. Go ahead and write it down. Okay, what do you think? What type of limosone is it going to be? Probably a convex. Is he right? Am I too predictable?
No.
Okay, 5 over 2 is bigger or equal to 2. It's not equal, but if it was, it'd still be convex. A divided by b is bigger than 2, so we have a convex polygon. Not polygon. Okay. Hannah Marshburn, where is the majority of our limosone going to be? On the right side, we have cosine in addition, so we have a majority of it on the right. And Molly, what's our max R value?
7.
7. All right, let's do this together. The cosine of 0 is 1, so we have 5 times 2 times 1. 7 zeros are first coordinate. The cosine of pi over 2 is 0. So at pi over 2, we have an R value of 5. The cosine of pi is -1, so we have 5 minus 2. The cosine of 3 pi over 2 is 0. And then at 2 pi, we're back at 7. All right. Now this one, you want to make round, and then it's kind of flat where you have your minimum distance from the pole. Whichever one is closest to the pole, you kind of want to make it look squished. Some of my students in the past have said this kind of looks like a guitar pick, which I think is kind of true, except it's a little bit more round down here. But it has kind of like that flat side like guitar pick would have. In my opinion, the most difficult part about limaçons is just remembering which type is